Morning, everyone. This is it, last day. How are we doing? Questions while we wait for others to come in? We will talk about curves today, absolutely. Yeah, we're going to finish up the integration business, and then we'll talk about curves. Curves will not be on the final, but will the exams be the same difficulty as the web work? No. No, the exam will be the same difficulty as the midterm, I think. Will the web work be switched to Tuesday? When is it due now? Quinn is asking, will the material covered today be on the final? That's the thing. We're going to finish up integration today. So the integration material you are responsible for. We're also going to discuss curves. I'll give you a small introduction to curves. Those will not be on the final. I'm asked to post the chapters we covered. In fact, I mean, I'll do that, but they're all listed on the course outline. I think we essentially covered everything that I posted on the course outline, but I'll post it nonetheless. Ranji is asking if today is the last day of class, what will happen from Tuesday to Thursday? Well, as you know, Tuesday is supposed to be a study day, and then Wednesday and Thursday are reserved for the final exams. So that is what it is. I'll be around Tuesday, Wednesday. If you have questions, email me. We can do that. If you want to get a Zoom meeting going, we can always do that. There's no issue. Just let me know. I mentioned 7 questions for the final exam. That is no longer the case. I finally wrote the exam, ran out of steam. There are only 6 questions. Quinn is asking if it's 48 hours long and not 72. There was some issues with that over the weekend. It's been resolved. 72 hours. So you'll have 72 hours as announced. Yeah. And only 6 questions. Now, I cannot stress this enough. You know, there have been issues on the midterm, some people complaining that they did not get all the marks, and that is because they did not show all the work. You have to show all the work. Again, using Wolfram Alpha is not a justification for any of the work there. So, I mean, look, while you are allowed to use it to test if your answer is correct. Whatever work Wolfram Alpha gives you, you're not allowed to use. The work on the final must be your own, nobody else's. So yeah, I mean, it'll open up June 4th at 9 a.m. and you'll have 3 days. Questions? Anybody? Why don't we start with a nice, very nice example. Very nice question, which finds its way onto the WebWork. Somebody's asking if it will be hard like 141. Well, I claim 141 was not that hard, first of all. Secondly, I'm going to suggest that it is comparable to the midterm. Slightly harder, because on the midterm, I mean, what had we done? We had done partial derivatives and sequences in series. So there was very little material. Here there's more material, a lot more material, right? So, and some of the material lends itself well to more difficult questions. Well, I shouldn't say that. No. If you know the material there, you'll do very well. So there's no issue there. 6 questions, they're all worth the same marks. Each question has equal weight. Let's go back to a nice example that I wanted to do and didn't have time. Consider this this question. Abe is asking, it took us half the classes to cover sequences, series, and partial derivatives. Will they represent half the questions on the final? I would like to say that they will represent less than a third of the questions. So at most 2 questions. Well, I mean, look, it's difficult to talk about partial differentiation because there's more than one question that has to do with partial differentiation, but it's partial differentiation and other things. Amar is talking about where we had a cone, and I think we were looking at something like this or whatever it was, and you're asking the question, it seems that phi is going from a negative value to a positive value, but you don't need that. Phi is measured from the positive z-axis coming down. So if you have this thing and you rotate it around 360 degrees using theta, you don't need negative phi's. And that's very important because you know that the Jacobian is rho squared sine phi. And if phi is negative, this Jacobian is negative. So you're going to need the absolute value when you make a switch to spherical coordinates. You want to stay away from negative phi values. In fact, when we introduced these spherical coordinates, we noticed that you could restrict your tension to rho being bigger than 0, theta in the interval 0 to 2 pi, and phi in the interval 0 to pi. You never need negative values for phi. You never need to go past 180 degrees, right? This is how phi is measured from the positive z-axis coming down. You don't need to go backwards there, right? You don't need to go here because you can rotate around using theta. That's the whole idea. And it's a very important observation. Let's go back to this. You may recall from Cal 2, Math 141, we did mention that this function does not have a simple closed form antiderivative. There is no elementary function which represents this antiderivative. This integral, however, is of tremendous importance. If you graph the function y equals e to the negative x squared, right, for large positive values of x, this is e to the negative infinity, which is 0, and same for large negative values, right? So as x goes to infinity, this gets closer and closer to 0. This is always positive, and you can graph it. This is what it looks like. This is your old friend, the bell curve. When people talk about curving an exam, that's what a lot of people use. This is a very important function in probability. This is a very important integral in probability. Associated to the normal distribution. However, what is that integral? There's no simple antiderivative. How do you evaluate this integral? You can evaluate it using a nice, slick trick. We're not going to evaluate that integral. We're going to evaluate the square of that integral. In other words, that integral times itself. Now you know x is just a dummy variable here. So whether it's x, or it's t, or it's s, or it's y, it's the same integral. This value is the same as that value. Now let's combine these into a double integral. Well, I mean, that's not easier. Or is it? Right? Here you have this x squared plus y squared business if you factor out a negative, which suggests switching to polar. If we switch to polar, x squared plus y squared, you know what that is. That's r squared. Jacobian, dr theta. Well, what becomes of the bounds then? What region is this? In polar coordinates, y goes from negative infinity to infinity, x goes from negative infinity to infinity. So it's all of the xy plane. It's all of R2. Tony is asking why we would have two variables after squaring it. Well, I mean, it doesn't matter, right? This is the same as that. It's just a dummy variable. So whatever value you get will not depend on whether you're integrating with respect to y or x or s or t or u or any other variable that you want to use. Right? So now we understand that here we're integrating over the whole xy plane. So what we need to do is now describe this in r and theta. And if you take if you let r go from 0 to infinity and you rotate that around 360 degrees, you will touch every point in R2. You can describe any point in R2 by taking some value of r between 0 and infinity and theta between 0 and 2 pi. There are no thetas anywhere, so we can integrate with respect to theta. This antiderivative for that, minus 1/2 e to the minus r squared between 0 and infinity. It's really an improper integral, but you know how to deal with that. We're going to relax that now, right? We're no longer in Cal 2. You know that it's really the limit as n goes to infinity of the integral from 0 to n. So I'm going to write infinity here with the understanding that it's really a limit. And what happens as r goes to infinity? This goes to infinity. E to the negative infinity is 0. So when you plug in infinity, the whole thing is 0. Minus plugging in 0. So minus minus gives you a positive, and you have pi. The integral squared is pi. So the integral is the square root of pi. Isn't that amazing? Who would have thought that the trick to evaluating this integral is to actually evaluate its square? How do we find the bounds for r? Here's the idea. From this integral, you understand that you're integrating over all of R2, the whole xy plane. We're switching the polar coordinates. So now we have to describe the xy plane using polar coordinates. So I'm suggesting if you let r go from 0 to infinity and you rotate that around, you will touch every point in the xy plane. And that's enough. We take the positive, Yishen is saying we take the positive square root because e to the x squared, e to the negative x squared is positive for all x, right? Exactly, right? I mean, the square is pi, so the integral itself is the square root of pi plus or minus, is a good point, plus or minus, but of course you know that this integrand is always positive. So we would expect a positive answer, and that's why we take the positive square root. Correct. If we had used x is r cos theta in the first place instead of squaring, right, x is r cos theta, but now you have two variables. So are you making a change from a single integral into something that has two variables? Questionable here. And how would r and theta vary? I'm going to let you think about that. Amar is asking if we can extend this method for any single variable integral. Well, I mean, you can always. It's not clear that you get anything. It's not clear that this is going to work for any other integral, but I'll invite you to try your hand. Try your hand at that, see what happens. Maybe this is a trick that extends. Maybe. Try it. Cecilia is suggesting that we could also use Taylor polynomials. Indeed we could, right? Indeed we could. Speaking of which, here's the question that I just changed last night. Originally, this was going to be a question on the final where I was asking you to approximate this so that the first two decimal places are correct. I changed it, so that's what it was going to be. Yeah, so Cecilia is suggesting we could have used Taylor polynomials. You could have. The problem with Taylor polynomials is that you're going to get an approximation. That's what happens. You get an approximation, not the actual answer. So it's fine if the question is asking you to approximate. Can we use that also for the series 1 over n squared that is equal to pi squared over 6? I don't know that you can. I don't know that you, but well, I mean, look, I've never seen that used there in that context, but try it. Try it. Maybe you have something there. If you have a nice proof that the series 1 over n squared converges to pi squared over 6, that would be very nice. That would be very nice. Because, well, I mean, you know, speaking of that, I wasn't going to mention anything because, you know, I suggested that the proof that the series 1 over n squared converges to pi squared over 6 was a bit beyond us, and you normally see it in a course on differential equations. However, there's a very famous proof by Apostle which uses only the double integral in the following way. if you look at the function 1 over 1 minus xy, which is really this, using geometric series. And then you integrate this over I want to say you integrate it over this square. And why am I saying that? If you do a double integral, this is going to be, right? I mean, this is x to the n, y to the n. So the antiderivative with respect to x is 1 over n plus 1, x to the n plus 1. And so I guess 0 to 1. I'm still missing a y to the n and a summation here. And when you integrate it with respect to y as well, essentially you get 1 over n plus 1 squared. Right. So now you were on the square 0 to 1. So not this, but that. So on the square, let's call it s. And what they did here was shift the square to there, to this thing via transformation, and evaluated this integral, and then got pi squared over 6 for that integral. It was very unexpected. So Apostle proved that in the 60s or 70s. Very unexpected, and a nice, simple proof that of that result. But if you have another one, that would be very nice as well. It's the shift, it's the rotation that's non-trivial here. And this is the kind of thing we're going to talk about right now, namely other changes of variable. Other changes of variable in double and triple integrals. What have we seen? Polar coordinates, cylindrical coordinates, spherical coordinates. These are only 3 examples. You can essentially just do any other change of variables you want. You know the result as long as you throw in the absolute value of the Jacobian, you're good to go. Let's see a few examples. Let's take a moment I think I may have mentioned the author's name wrong. It might be apostle like this, T-O-L, not T-L-E. Anyways, doesn't matter, but let's draw the region we're talking about here to understand really the significance of this question. So one vertex at -1, 3. Another vertex at 1, -3. Another vertex at 3, -1. And one last vertex at 1 and 5. So this will go through the origin. All right, consider this. Look, I mean, you have options, right? You don't need to make any switch. Again, the idea behind switching to a different coordinate system is that it makes things easier for you. If it's not making it easier, don't do it. You can integrate this with respect to x and y here, right? Suppose you set it up dy dx. It's doable. Nothing wrong with that. How would you set it up? How does y vary? Y goes from here to there. For a while until you hit this thing. Well, in this case, they both happen to be the same, so it's not too bad, right? So y would go from this bottom line to the top line for a while, and then this bottom line to that top line. But you can imagine a scenario where instead of 1, 5, this could have been 2, 6, right? So right here, and this could have gone back down to here. So it would have gone from this line to the top line for a while until you hit there. And then this bottom line still to the same top line until you hit the vertex, and then bottom line to that top line. So in this case, you break it up into 2 pieces, but you immediately realize that it could have been worse, and you could have had to break it up into 3 pieces. 2 pieces, not so bad. 3 pieces, a lot more work. Is there a way for you not to split it up at all? Let's figure out what these lines actually are. This is the line y equals what? Negative slope going through the point 3 minus 1, minus 1, 3, and 1 minus 3. Well, let's work it out. When x is minus 1, y is 3. And when x is 1, y is minus 3. So if you add these two together, you get that b is 0. And if b is 0, m is negative 3. In other words, you have the line, this line, y is minus 3x. Very nice. And this line, I claim is going to have the same slope. And when x is 1, y should be 5. So it's going to be plus 8. Let's make sure it goes through this point here as well. When x is minus 1. No, something's wrong. No, so what am I doing? When x is 3, this is minus 9, plus 8 is minus 1. Very nice. So this line goes through those 2 points, right? When x is 1, y is 5, and it goes through there as well. And over here, when x increases by 2, the height increases by 2. So the slope is 1. And when x is minus 1, y should be 3. So x plus 4. Does it work for the other one? 1 plus 4 is 5. Looking good. And finally, this one here. Same slope. When x is 1, y should be minus 3. So minus... Sorry. Let's check that it works for here as well. When x is 3, y is minus 1. Very nice. All right, so let's clean that up. What are we saying? This is the line y equals negative 3x. There it is. Or the line, if I bring the 3x to the other side, 3x plus y equal to 0. If I bring the 3x to the other side, 3x plus y equal to 8. And if I bring the x to the other side, minus x plus y equal to negative 4. And over here, minus x plus y equal to 4. And this is suggesting the following transformation. It's suggesting to let u be 3x plus y. Right? Because here you have u equals 0, u equals 8. And then v b minus x plus y. So this line segment is v equals negative 4 to v equals 4. So you see, by making this transformation, it transforms this parallelogram in the xy plane to a rectangle in the uv plane where u goes from 0 to 8 and v goes from negative 4 to 4. So I said rectangle, but it's actually a square. Well, now it looks like a rectangle. Right, so it transforms this parallelogram in the xy plane to a nice square in the UV plane. So now, if you make this transformation, you don't have to split up the integral into 2 or 3 pieces. Just one simple, easy integral will do the trick. But now, as you know, when you make a change of variables, you need to calculate the Jacobian. The Jacobian, which is dxy by duv. Or dx du, dx dv, dy du, dy dv. But you don't have x and y as functions of u and v. You have u and v as functions of x and y. Well, two things. Either you solve for u and v as functions of x and y, or I mean rather x and y as functions of u and v, or theorem, dxy by duv is 1 over duv by dxy. As long as the denominator is not 0. So either way, in this case, why don't we do both to convince ourselves? I'm offering this without proof. Well, let's do it, see what happens. And let's see what I mean. Right, so what could you do here? You could multiply, well, you could subtract, right, this minus that. Right, so if you do u minus v, this minus, so 3x minus negative x, that's a 4x, and then y minus y is 0. So x is u minus v over 4. That's easy to see. And whatever you want, right? Here, y, which is v plus x, that's v plus this, which is u minus, no, u plus 3v over 4. So if you solve for u and v, then it's very easy. Your Jacobian let's say this so that there's no so dxy by duv, what is that? Dx du, x is right here, so dx du is 1/4. Dx dv is minus 1/4. Dy du is 1/4. And dy dv is 3/4. What is that? This is 3 over 16 plus 1 over 16, which is 4 over 16, 1 over 4. Your Jacobian is 1 over 4. Let's work out, just for fun, duv by dxy, just to see the relationship, right? Just to convince ourselves of this relationship here. This is du dx, du dy, dv dx, dv dy, du dx is 3, du dy is 1, dv dx is -1, and dv dy is 1. And this is 3 plus 1, which is 4. So you see, dxy by duv is 1 over duv by dxy, exactly as suggested by the theorem. So the integral over your parallelogram, we're going to make the switch to u and v. X is u minus v over 4. Y is u plus 3v over 4. Jacobian du dv, where u varies from 0 to 8, v varies from -4 to 4. Let me pull out the 1/4. These cancel out, so that is u minus v. These cancel out, leaving you with a 2. So that's 2u plus 6v du dv. V varies from -4 to 4. This is odd in v, and this is odd in v, so these integrate to 0. Yishen is asking why we need to switch the diagonal elements. I'm not sure what you mean here. Which diagonal elements are we switching? Quinn is asking, what if we did not get these same equations? How would we have found the substitution to apply? Well, that's the thing, right? I mean, if there's no relationship, then either you probably should not be making a change of variables, or possibly the change of variables is harder to see. Again, these change of variables are only there to help you if you're not seeing what to do. Maybe there isn't one, and maybe you shouldn't waste any time working something out. In some special cases, some questions will tell you what substitution to make, but in this case, I claim it naturally arose. duv by dxy, didn't we switch the position of du dy and dv dx. I want to say we did not. It's the first variable on top, second variable on the bottom. Here, this is dx du, dx dv. So first variable on top, and then second variable on the bottom. dy du, dy dv. First variable on top, second variable on the bottom. And then you have the integral. So let's finish that up just for completeness. There's no more v anywhere, so this is going to be 8. And you've got 3u, which is 3 over 2u squared from 0 to 8. So this, that, and that cancel out. 64 times 3, 18, 19, 19, 2, 192. I want to say 192. Ivan is asking, is it coincidence that the reciprocal of the derivative notation for the Jacobian gives an answer that is also the reciprocal? Well, that's what that theorem was suggesting. It's exactly right. I mean, I've rubbed it off now, but that theorem was exactly saying that. So not coincidence. As long as the denominator is not 0, right? Yishen. Remember how we denoted it? dxy by duv dx du dx dv dy du dy dv. That's how we introduced it. In fact, here's the thing. It actually doesn't even matter. It doesn't really matter. As long as you are actually consistent. Well, let's not say that it doesn't matter. Let me take that back. The real definition is this. So I don't want there to be any confusion. This is the real definition. How is this related to dx du, dx dv, dy du, dy dv? Because that's what you want to write, right? You want to leave the bottom the same and change the top. So how are these two things related? Exactly as Prince suggests, it's a transpose, right? This is the transpose of that. And you know that the determinant of A is the same as the determinant of A transpose. So it actually doesn't matter. It actually doesn't matter. But the real definition is this. Vivian is asking if we can go over how to find the expressions for u and v. These ones here, you mean? we looked at the, we drew our parallelogram, right? So, I mean, that was the important first step. We drew our parallelogram in X and Y. And those straight lines actually had equation y equals negative x, negative 3x, y equals negative 3x plus 8, and this was y equals x plus 4, and y equals x minus 4. Or, if you bring all the x's and y's to one side, this is minus x plus y equals 4. This is minus x plus y equals negative 4. Bring this 3x to the other side. This is 3x plus y equal to 0. And 3x plus y equal to 8. And you see that they arise naturally. They arise naturally. I'm letting one of them be u, the other one be v. Let's take another example. Ishan is asking why du dx is 3 and not 1 over dx du, which is 4. Short answer to that is that there's not enough information contained in in du dx or in dx du. Meaning that, right, I mean, if you look at du dx, it's understood that u is a function of x and some other variable. And that other variable, anything can happen. Because in du dx, you just have the derivative in the direction of x. Anything can happen in the other direction. So that's why there isn't necessarily a relationship between du dx and dx du. Yeah, let's say that. Let's take a moment here to graph these, see what happens. Just a rough graph. It's actually not really necessary here, but it's nice to see why you wouldn't want to immediately integrate with respect to u to x and y. Right, the first one, y equals 1 over x, you know what that looks like. I regret having drawn that. Let me draw it again. Blue is asking, why is it that when we got rid of v for being an odd function, the integral relative to v was completely removed? Not the integral itself, just the v business. And then you integrate with respect to v, which was going from -4 to 4, and that's where we got the 8. It does still affect. It does still affect, but there aren't any v's anywhere. So by Fubini's theorem, you can integrate with respect to v first, and you get 4 minus -4. So that's where the 8 comes from. So let me draw that again. Y is 1 over x. Well, it was fun the first time. I don't know what else. X. And then y equals 2 over x is the same thing, but it's always larger. And then y is 1 over root x. Which is going to so here y squared is 1 over x, let's say this, and here y was 1 over x. So these intersect at 0 or 1. So it's going to intersect at 1. And when does it intersect the other? 1/2. So y squared is 1/2 y. So it intersects when y is 0 or y is 1/2. All right, so maybe something like this. And then you're gonna, and it's gonna be the same thing but higher. So, you know, something like this. Anyways, it's a bad graph, but it gives you the idea of what's happening. In other words, if I was to set this up using x's and y's, y would vary from here to there for a while until you hit this point, and then it's here to there for a while until you hit that point, and then it's here to there. So you have to break it up into 3 pieces. right? Let me blow that up again if you're not seeing it very well. I don't know why it's increasing now, but you get the idea, right? So here to there for a while until you hit that point, and then here to there for a while until you hit that point. In other words, 3 regions. Do we care about the branches in the other quadrants? It's a valid question, right? What happens if both x and y are negative here? You have that happening there, but not here, right? Here, x cannot be negative. So you don't have anything on the other side, right? Because if x is negative, since this is always positive, this side would be negative, and it cannot be equal to a positive number. That as well, as Quinn suggests, it would not be defined if x was negative. Very good. So my point is, if you set that up using x's and y's, you're going to have to split it up into 3 pieces. However, this question itself really is suggesting a change of variables. Right? If you make the change of variables, u equals xy, v equals xy squared, then this change of variables is transforming this, I don't know what to call this kind of skewed parallelogram, if you will, in the xy plane. It's transforming that into what? U equals 1, U equals 2, V equals 1, V equals 2. A nice square in the UV plane. Very nice. The only thing you need to worry about is, once again, the Jacobian. All right. Well, let's work it out. Again, you have options. You have options. You have options. What do you want to do? You can solve for u and v. Let's do it. Right? You see what's happening? This divided by that is just y. So that's very nice. And if y is v over u, then x, which is u over y, so u over v over u, which is u squared over v. And you know, Yishen, you're back to this du dx is not equal to 1 over dx du. Were you the one that emailed me about the differential equation there, df dx squared plus df dy squared, in terms of some other thing, that might have been the issue we were having, right? And I think that answers that question as well. Exactly. Du dx is not the same as 1 over dx du. But the Jacobians themselves are related in that way. So not the individual components, but the whole Jacobian itself. Let's work out dxy by duv, right, the Jacobian. So dx du, well, let's write it out so there's no misconception here. That's not it. Dx du, dx dv, dy du, dy dv. So dx du to u over v. Dx dv is negative u squared over v squared. Dy du is negative v over u squared. And dy dv is 1 over u. What does that give us? 2 over v minus minus minus. The u squares cancel. So that is just 1 over v. 1 over v, which is positive, right? Because you are in the interval 1 to 2. So we're good to go there. So what happens? Y is this. So y squared is v over u squared. Jacobian du dv, where both u and v go from 1 to 2. So the Jacobian is y squared x. Well, I mean, right, I mean, the question, let's do it the other way. Let's look at duv by dxy to see if they are related. So that is du dx, du dy, dv dx, dv dy, du dx is y, du dy is x, dv dx is y squared, and dv dy is 2xy, which is 2xy squared minus xy squared, which is xy squared, exactly as predicted by Brun there. And so if we look at 1 over xy squared, xy squared is actually v, which is 1 over v. Exactly as suggested by the theorem. Very nice. Amar is asking if we had the interval from -2 to 2, would we have to split the Jacobian up into 2 parts? Because it's an improper integral. Is that what you're saying here? You'd have to be careful, right? Yeah, you'd have to be careful. You'd have to be careful, very careful, because when v is 0, something breaks down here. So let's say that in practice this is not going to happen to us because something fishy happens at 0, whereby you might not be able to go from one coordinate system to the other. So we'll stay away from that. All right, let's integrate. This is v over u squared, du dv. Integral with respect to u. V is outside, minus 1 over u, from 1 to 2. So this is 1 minus a half, which is a half. And then the integral with respect to v is 1/2 v squared, from 1 to 2. So that's 1/4, 4 minus 1, which is 3, 3 over 4. Right? As Tony points out, the Jacobian cannot be 0. Well, that's the thing, right? So, I mean, Jacobian of 0 is going to be an issue. We don't want that. We don't want that. That means that you cannot go from one coordinate system to the other. And, you know, there it is, right? I mean, we have 4 lines here. Once we decided to make the change of variables. If you did not make the change of variables, you would have an integral which isn't that difficult to integrate, but I claim it would be a bit longer, and you'd have to break it up into 3 pieces. So it would easily be 3 times as long, at the very least. There it is. How are we doing with that? Questions? Questions, anybody? This is pretty much it for integration, unless you have any questions. Nobody? Moving on. Amar is asking if the bounds have both negative and positive values of v, since your Jacobian is 1 over v, you would have to take the absolute value. I mean, it's always the absolute value, right? In this case, the absolute value signs were not needed because you knew it was positive. But it's always absolute value of the Jacobian. So if your v is going from positive to negative values, or negative to positive, I should say, then you're going to have to split it up. Absolutely. right? You'd have to split it up in order to get rid of the absolute values. It's the first thing you need to do before you integrate. Questions? Let's move on to curves. It's going to be just a small introduction to curves, just to get you acquainted with these for people who are going to do advanced calculus. I mean, you're not missing anything. There's not going to be any knowledge essentially that's assumed, but let me show you what's coming up. And it's nice to get acquainted with these now so that when you jump into them later on, you'll have an idea of what's happening. I mean, what are curves? You know what curves are, right? I mean, if you have a function, this is a curve. This is a curve. And you know, I mean, in Cal 1 we were looking at the derivative at every point. And in Cal 2 we were looking at the area underneath the graph. Omar is asking if curves will be on the final. They will not. No. And we saw a generalization of this, right? Because of course, if you have a function, you have the vertical line test, which tells you that any vertical line cannot intersect more than once. So this is a very special kind of curve represented by functions. We looked at polar coordinates, which allowed us to draw curves which were not functions. Right, I'm thinking about these petals. Right, we saw these kinds of petals happening. Right, and these were not functions because, again, vertical lines intersect more than once. But this gave us a different notion of curves, different examples. What are curves? Well, curves are one-dimensional objects, right? Very much like this, where here every point on the curve could be described in terms of one variable, right? The x and y components can all be written in terms of x. Here, if this was in polar coordinates, every point here, right, you know that the x and y coordinates are r cos theta and r sine theta respectively. So f of theta cos theta, f of theta sine theta, right? R cos and r sine were the polar coordinates. And here, each of the components, every point on the curve, can be written in terms of one variable theta. Let's generalize this idea. That's the idea we want to generalize. A curve is a one-dimensional object where every point on the curve xy or xyz right? If it's a curve in the xy plane or a curve in 3 space, or you know, this generalizes curves in 4 space and 5 and Rn in general. So one-dimensional object where every point on the curve can be described using one variable. Usually denoted by t. In other words, the x component is a function of t. The y component is a function of t. The z component is a function of t. And so on if you have other components. Let's illustrate. So R of t is the usual notation to describe curves. So let's take this example. R of t is cos t sine t. Of course, you recognize this as the polar coordinates, where r is 1. So from your knowledge of polar coordinates, you know that t is measured counterclockwise from the positive z direction. So all of these points live on the circle of radius 1. Right? When t is 0, you're here. And as t increases, you move along your curve in this fashion. There it is. Imagine, let's take the same example, but let's now throw in a z component. Cos t sine t, t. What's happening here? Right, if that t wasn't there, this would just live in the circle of radius 1, right? Again, it's the same polar coordinates there. Where r is 1, this would live on a circle of radius 1 in the xy plane. But now you have this z component of t. So, you know, you're living on this circle of radius 1, but now it's moving up as t increases. So you're starting here, right, at the usual start. But not only are you going around in a circle this way, but you're also going up at the same time. Some sort of helix, if you will. Right? Imagine one of those slinkies that you're pulling up. There it is. But you know, I mean, you've seen these before. Let's take an example you're familiar with. Consider, Yushen is asking, the axis represents the original variables x, y, z. Could you repeat again from the graph, can change of t, can the change of t be represented? Well, all I'm doing here is seeing how, I mean, really, I'm just plugging in some points for t, but you bring up an interesting point, namely, how does the change in t, how is the change in t represented? And when we talk about change in t, we're really talking about the derivative, right? So maybe your question is, if we have this curve here, can we talk about the tangent line at any point? Right? Certainly makes a lot of sense. But before we get to that, all I'm saying is, if you start at t equal to 0, you're starting at the point 1, 0, 0. And as t increases, the x and y coordinates live on a circle of radius 1, centered at the origin in the xy plane. And then, right, so the image, you're always restricting your attention to points here, and then you're bringing them up via this t thing. So when t is pi over 2, you're up pi over 2. At pi, you're up pi, and so on and so on. The idea of differentiation will come in momentarily, but before we do that, let's consider one more example or two. Let's look at the line segment. From the point 1, 2, 3 to the point 1 minus 2, 1. Yushen is asking if we're going to move downwards. If the t is negative, that's fine too. You can do that. Absolutely. Right? So there's no real reason to restrict your attention to a positive value of t. T is allowed to be negative. And in that case, you'd be going downwards. Absolutely. Let's look at the line segment. From this point to that point, it's a line, so you know what you need to describe a line. You need a point and a direction vector. The direction vector is going to be the vector PQ. So that minus that, 0, minus 4, minus 2. And the equation of the line is the point plus t times the direction vector. And when t is 0, you're at that point. And when t is 1, you're at that point. So you see that this describes the curve 1, 2 minus 4t, 3 minus 2t, where t goes from 0 to 1. This is the collection of points on the line segment. Every coordinate is described using one variable t. So we have this curve, this line segment, this one-dimensional object. There it is. Let's look at one more. Because somebody had suggested earlier curves of intersection. Yushen is asking, can T be outside the range of 0, 1? Well, indeed it can, but then you'll be outside of the line segment joining the 2 points. So theoretically, there's no issue with that. In this particular case, I think we wanted to restrict our attention to the points joining, to the line segment joining those 2 points. Brun is asking, so we need to find the parametric equation in order to express our functions in terms of t. That's one big question in curves. How do you describe your curve? Right here, we've described the curve using one parameter only. That's one of our goals. This is known, as Brun suggests, known as a parametrization. This describing of the curve using one variable only is known as a parametrization of the curve. Parametrizations are not unique. You may have many ways to describe your curve, some better suited than others for whatever you want to do on those curves. Let's take this example here. This will illustrate very nicely the idea of different parametrizations. Back to Brun, who says if we find 2 points of our function, we can find the parametric equation, therefore always expressed in terms of t. It's not always that easy. Take this example here. Take this example. Try to parametrize that before we do anything. While you're doing that, let me take a moment to actually draw what's happening here. X squared plus y squared equal to 1. Well, I mean, we've seen that many times. You know what that is. This is a circle in the xy plane. Circle of radius 1, centered at the origin. And there's no z value specified. So it's that circle stacked one on top of each other in the direction of z. It's a cylinder. It's a cylinder. And then this you recognize as a plane. As a plane. It's a straight line in the YZ plane, but again, no x is specified here. So think of stacking these in the direction of x. So you have this cylinder that's being cut by this plane. And so your curve of intersection right? Imagine you see what's going on, right? We have this cylinder. You have this cylinder, and then you're cutting it with this plane here, like that. So cut it. There it is. And that's your, that is your curve of intersection. Right, that's just where the two intersect. Right, so just this curve here. So that's what we want to describe using one variable only. Right, it's a one-dimensional object, so you should be able to describe it using one variable. So wait, Nintendo is saying the intersection is a straight line. No, not a straight line. Some sort of ellipse, maybe. Ellipse on a slanted plane. Right, you have your cylinder and we were cutting it. So set, Yishen is suggesting set z equal to t. A very nice suggestion, right? And the curve lives on both of these objects. It lives on the plane and it also lives on the cylinder. So if it lives on the plane, then the y, which is 2 minus z, is therefore 2 minus t. And here it also lives on the cylinder. So x, which is plus or minus the square root of 1 minus y squared. So x is going to be plus or minus the square root of 1 minus 2 minus t squared. You have to break it up into two pieces in this way, right? This half, which is in the positive x, and then the other half corresponding to the negative square root. But there it is, right? So if I call this C1 and C2, the two halves of the curve, then to describe C1, my description using the one variable t, I'm going to use a positive square root here for this half. So x is that, y is 2 minus t, and z is t, where t varies from what to what? When y is -1, z is 3, And when y is positive 1, z is 1, so t varies from 1 to 3. And C2 similarly. So here, our parametrization, we had to split it up into two pieces. Not a big issue. And we can essentially do whatever we need to do. Brun is asking how I got the bounds for t. I suggested that we were going to look at how y varies, right? So instead of looking at how z varies, let's look at how y varies. This is your y coordinate here. Y has to live on the cylinder or in the circle of radius 1. So the smallest value of y is -1, and the largest value of y is +1. So the largest this gets, right? This is the y. This is always between -1 and 1. So if I subtract 2 from everywhere, add a -2, -1 minus 2, 2 minus t minus 2, 1 minus 2. So this is -3 less than -t less than -1. And now multiply the whole equation by -1, multiply by a negative, so I switch the order of the signs. 3 bigger than or equal to t, bigger than or equal to 1. T is between 1 and 3. Will it be the same if you set y equal to t? Right? I mean, Yishen is suggesting another parametrization. If instead you had set y equal to t, in which case z would have been 2 minus t, and x would have been plus or minus the square root of 1 minus t squared, then t would have varied from -1 to 1. Very nice. Very nice. So you see, this would be another parametrization. We still haven't stumbled on to the important parametrization here, one where you don't need to split it up into two pieces. Let's look at this cylinder or this circle of radius 1. How would you describe efficiently this circle of radius 1? Polar coordinates does precisely that. Polar coordinates where r is 1. So x is cos theta. Y is sine theta. This describes very effectively the circle of radius 1. And if y is sine theta, z is 2 minus y, 2 minus sine theta. So you have this nice parametrization here in terms of one variable, theta, where you don't need to split it up. You don't need to split it up into two pieces. And each of the components is very simple. Very nice. Now the question comes up naturally. What about tangents? Right? The question naturally came up in Cal 1 when we had y as a function of x. What about the tangent line? So here, if you have a parametrization of your curve in one variable, what about the tangent line? Can we come up with some sort of analogous extension of the derivative, essentially? Well, why don't we try exactly the definition we know? Right? This is a function of one variable. So dr dt let's look at the limit definition and try to understand what would come out of that naturally. This is r of t plus h minus r of t over h. Right? If we just blindly apply the definition of the derivative, this is what it is. But what is that? Here, your r is really made up of components, right? This is x of t, y of t, maybe a z of t. So this, what would that be? Well, this would be x of t plus h, y of t plus h, z of t plus h. The whole thing over h. And if we group this together, let me leave the h outside as a 1 over h. This is x of t plus h minus x of t. And if I multiply the 1 over h into this, right, because this can be treated as a vector. So this is x of t plus h minus x of t over h. And same for the y and same for the z. Wow, let me not be lazy here and let me write it. And same for the z. And then if you take the limit inside, right, because now this is just a regular function. So x of t plus h minus x of t over h, limit as h goes to 0, you know exactly what that is. That's the real definition of the derivative. When your function is just a function of one variable, and that's exactly what you have here. So if you bring the limit inside, this is x prime, y prime, z prime if you have it, and so on and so on. So now we have a way to talk about the derivative. If you have a parametrization where each component is a function of one variable, the derivative, you just differentiate every component. One question that arises naturally, does this coincide with the derivative of a function? Because we saw that functions are really themselves special cases of a curve. Let's take an example of what I mean. Y equals x squared. You know what's happening here. You know this function. Right? Well, Tony is asking, is a curve a vector? I mean, it depends how you want to see it. There are several ways to see it, right? In the same way that you can sometimes confuse a point xy with the vector emanating from the origin to that point, you can do the same for curves. You can view this as the collection of points, or you can view it as a vector as well. So there are a few ways, and you can go back and forth depending on whatever situation suits you. Let's take this example, y equals x squared. You know that dy dx is 2x, and let's take, let's find the tangent line when x is 3, and when x is 3, y is 9, and the tangent line y equals mx plus b, you know that the tangent line has slope 6, right? So this is 6x plus b, and when x is 3, y should be 9. So b is easily seen to be minus 9, and y is 6x minus 9. This is the equation of your tangent line at x equals 3. Good. What about in this scenario? What about in the scenario where you parametrize that curve? Right? The whole idea which gave rise to that was that if you have x and a function of x, everything is described in terms of one variable, right? So t squared. Every every point on this parabola has coordinates x squared, or t squared. It can be an x, it can be a t, it doesn't matter. Like I said, it's customary to use t, but really the point is one variable. Take the derivative the way I just erased it. It's the derivative of every component. What is the derivative? The derivative of t is 1. The derivative of t squared is 2t. Let's look at the derivative when t is 3. When t is 3, you get the vector 1, 6. And let's look at the line with equation. Well, let's look at the line going through the point 3, 9 with direction vector 1, 6. Right, so the line with this as direction vector is right here. And if you solve for t is x minus 3, and plug that into here, six x minus 9, right? So you have y equals 6x minus 9, exactly your tangent line. So this is a vector tangent to the curve. Right? At the point 3, 9 right here, this vector is tangent. This vector 1, 6, or this vector, the derivative, is tangent to the curve. Yishen wants me to repeat how we got x is 3 plus t. All I'm saying is we took the derivative and we got this vector 1, 6. Treat that vector as a direction vector to the line. As a direction vector. I want to know what equation of the line goes through the point 3, 9 with this as the direction vector, right? 1, 6. So going through the point 3, 9 with direction vector 1, 6. So there it is. That's the equation of your line. And that turns out to be exactly the tangent line. So r prime is tangent to your curve. Let's write that down. R prime is tangent to the curve. Let's take this a step further. And let's define a unit tangent. We define the unit tangent the unit tangent vector to R as R prime over its length, if the derivative is not zero. So you see what we've done? We have defined, right? We saw that the derivative gave us a tangent vector. Now I'm defining the unit tangent by dividing by the length. What does it mean to be a unit vector? It means that the length of t is 1. And if I square both sides, it's still 1. But the length of t squared is the same as t dotted with t. So t dotted with t is 1. Now, I mean, you understand here that t is going to be some complicated vector where each of the components depends on t, and you're dotting it with itself. Differentiate the whole equation with respect to t. What happens? Well, certainly on the right, the derivative is 0. What is the derivative of t dotted with t? Understand that t is some function, right? It is some vector where the first component depends on t, the second component depends on t, the third component depends on t. I probably should not use x, y, and z so as not to confuse you with r. Let me say f, g, and h. So what is t dot t? If you take this vector and you dot it with itself, what do you get? Well, you get f squared plus g squared plus h squared. Right? So now what's the derivative of that? What's the derivative of this business? Well, it's something squared. So 2f times the derivative of the inside. 2g times the derivative of the inside. 2h times the derivative of the inside. If you take a step back, there's a 2 everywhere. So this is f prime, g prime, h prime, which you might recognize as fgh dotted with f prime, g prime, h prime. Or this, which is the original t, and this, which is the derivative of every component, which is exactly how you take the derivative of t. So the derivative of the dot product is twice times t dotted with t prime. And if you divide by 2, you conclude that t dotted with t prime is 0. What does that mean? That means that the derivative of t is orthogonal to t. T primed is orthogonal to t. Isn't that nice? Beautiful, slick observation. So let's transform that into a unit vector. And we define n as normal. We define n, the unit normal, to be t primed over the length of t primed. So let's understand what's happening. You have some curve. R of t. We found that the derivative was tangent to the curve. So by evaluating this, at any point, we get a tangent vector, a unit tangent vector. And then we just saw that the derivative of the unit tangent is orthogonal to t. And we use that to define a unit normal vector. And now, if you have two vectors, you can find a vector orthogonal to both of these by taking the cross product. And this is going to be orthogonal to both of those. Exactly. Thank you, Tony. Right-hand rule, you're going to have a, that's too big. You're going to have a vector B orthogonal to both of these. And so you see what's happening. For every point, you have this collection of 3 orthogonal vectors. T N, and B. Together, T, N, and B formed what is called the Frenet frame. And by studying how these vectors behave on your curve, you in turn study the curve itself. Since these three vectors are orthogonal and you're living in R3, they're going to form a basis for R3. And consequently, any vector can be written as a linear combination of these three basis elements. In particular, observe that B itself is going to be a unit vector. So B dot B has to be 1. And if you differentiate the whole thing with respect to T again, you see that B dot B prime has to be 0. So B prime which had to be a linear combination of Tn and B, since B dot B prime is 0, if you take the dot product of this with B, this is 0 and that's 0, but this is not 0. Right? If you take the dot product of this with B, you get 0, but here you get A times T dotted with B, which is 0, plus B times N dotted with B, which is also 0, plus C times B dotted with B, but that's 0, and this is 1. So C has to be 0. In other words, B prime must be a combination of only T and N, and you can repeat with a few of the others. All I'm saying is, associated to this Frenet frame, you have the notion of curvature and torsion, which is one of these components, one of these coefficients of T and N. And again, the point being that by studying how these vectors behave on the curve, you study the curve itself. This is the beginning of the subject known as differential geometry. And you can take a whole course on that topic, but that's where it begins. So there are a lot of these nice proofs and observations, but that's the idea. In advanced calculus, you don't need that much. All you need is the fact that the derivative R prime is tangent to the curve. That's all that's required, and you're good to go. How are we doing here? Any questions? Seems like a good place to end. Thank you all for coming. Are there any questions? This is our last class. I'll be around tomorrow if you need anything. Did we not cover any material that we were supposed to cover in 262? That would serve, no. We covered everything we needed to cover. We're all good. So R is the double derivative to the curve. I don't know what R you're referring to. R here is the actual curve itself. Well, right. So, I mean, I only threw that word out, curvature. There's also something called torsion. Yeah. So, I mean, the idea behind curvature, not that you need it for 264 per se, but it measures how much your curve curves, if you will. Yeah, so it's a measure of how much your curve curves. So T is the double derivative again, not really, right? T is just the derivative over the length. Avery's asking, what is the difference between a type of question we would be asked where we use the regular max-min strategy versus Lagrange? Well, that's up to you, right? You know that Lagrange multipliers is only valid on the boundary. So you have options, right? I mean, if we're talking about in two space here, if you could parametrize your boundary in terms of one variable. That was the regular strategy, right? Describing it in terms of one variable, and then maximizing and minimizing your function on that boundary, or Lagrange multipliers. It gives you exactly the same answer as you would expect. Yishen is saying T prime is the double derivative. Okay, so now you're talking about T prime. T prime here, not the double derivative of R though, right? The double derivative of this quotient. So be careful with that, right? It's the derivative of this quotient, not the double derivative of R, not the second derivative of R. Yeah. Questions? Anyone? So thank you all for coming. And like I said, feel free to send me any questions. We can answer them via email or do a Zoom meeting if you want. YB dot B is 1. B is the cross product of T and N. So the length of B is the length of the cross product, which is length of T, length of N, sine of the angle between the two. T has length 1, N has length 1, and the angle between the two is 90 degrees. Sine of 90 is 1. So the whole thing is 1. So that's why B dot B is 1. Thank you, everyone. So, like I said, email me if you've got questions. Otherwise, good luck on your exam. Again, 6 questions. If you know the material, you'll do very well. Thank you all. You guys have a good one and a good summer if we don't speak from then onwards. All right.